Coulomb's law is just a part of a bigger picture and only helps to find the force between the two charges. Nevertheless, it does not inform about the causes of the force between these two charges. If you look at here, this is the force between two charges. As I have already discussed that this has a three part. One is the characteristic of the medium, we also call the Coulomb constant, and Q1 and Q2 is the magnitude of the charges. This R is of course the distance between these two charges. So in order to find the strength of the force between any two charges, we can use these equations. Charged particle produces force over a great distances, and one big question that how does a charged particle know another one in the vicinity of the one? I'll give you detailed answer about these questions in a later slide. And these questions generally introduces a new concept in electrostatics. We call it electric field, which is a new way of thinking about the Coulomb's law. Okay, let's focus on the leftover questions, that how does a one charged particle know the presence of another charged particle in the vicinity, or we can call it how can there be such an action at a distance between the two charges. So let's suppose we place a positive charge here, and immediately a line of forces evolve within no time and fill all of the space with the line of forces. So these line of forces, we call it the electrostatic field. Although I have given a few lines here, but in reality a huge number of lines around positive charge, and all lines is almost appears to be a continuous, which is called is the quasi-continuous. Of course, two lines cannot intersect to each other, but they are very close. Therefore, apparently, it looks like continuous line charge distribution around a positive charge. In the first scenario, if we bring a positive charge in the vicinity of these source charges, then a force is exerted by this charge through the electrostatic field around these source charges. And you already know that same charges exhibit a force of repulsive. Then if you allow this charge to move free from this point, then this charge freely move away from these source charges. In the second scenario, if we bring a negative charge in the vicinity of this source charge, then again a force exerted on this negative charge through the electrostatic field of this positive charge. And because unlike charges attract to each other, then if we allow this charge to move from this point, then this must be moves toward these positive charges. We can call it the force exerted on a charge due to other charges through the electrostatic field. So if we place a positive charge within the space, then a charged particle creates an electrostatic field in all space. Other charged particles sense the field and experiences a force in response to the source charges. And in this scenario, you must distinguish the source charge and the test charge. Source charge are those charge which is already present in the space that produces electrostatic field, and the test charge is the charge where we intend to find electrostatic force. Now let's define the electrostatic field in terms of the electrostatic force. So the electrostatic field is defined as the electrostatic force per unit charge, and this equation can be written as force, of course this is electrostatic force, is equals to charge time electrostatic field. But keep in mind, this charge is a test charge. So this is our second starting equation, and it's a vector equation that tells you magnitude and direction of the force. So the force can also be determined through the Coulomb's law. If you know the charges and the distance between the charges, then we can find the force by using simple Coulomb's law, as we have studied before. And if you know the electrostatic field, then we can also have this equation to find the force. The second important point is that the force on a positively charged object is in the same direction as the electric field at that point. And if you have a negative charge in the vicinity of electrostatic field, then the force on a negative test charge is in the opposite direction as the electric field at that point. As electric field is a measurable quantity, then we must define the unit. So electric field is measured in the unit of Newton per Coulomb. This is one of the electrostatic unit. So in addition to this unit, we can also define the electrostatic field in terms of the volt per meter. Keep in mind that the electric field direction is the direction of a positive charge would feel a force. A positive charge would be repelled by another positive charge. So therefore we can define the direction of the positive charge here. Let's suppose if we have already positive charge in space, and in the previous slides we learned that the line of forces is evolving from this positive charge in all direction. It started from this positive to the outward direction. On the other hand, if you have a negative charge, then the electrostatic field is again uh, in all region, but the direction of electrostatic field is towards this charge, because negative charge is considered as a sink of the charges. Now if we have a positive charge here, and let's suppose if we bring a positive charge, then a force between two positive charge would be repelled to each other. Therefore a positive charge is moving away from this positive charge. So this is the way to define the direction of electrostatic field. The idea of electrostatic field is not really new, because we have already studied before a gravitational field and the gravitational forces. You already know that there would be a force between two masses, and that is called the gravitational force, where capital G is a universal gravitational constant, and m1 and m2 is the magnitude of the masses, and r12 is the distance between two masses m1 and m2. So this is the force between two masses, and we can also easily derive this equation from the universal gravitational force. So this equation tells us that the gravitational acceleration is equal to the force per unit mass, and previously we call it the gravitational acceleration, which has a value of 9.8 over the surface of Earth, and it varies when we move either away from the surface or inside the Earth. So in principle, this is called the gravitational field because of the Earth gravity. The electric force is like the gravitational force. We call it the action at a distance, and the electric force can be thought of as being mediated by an electrostatic field. Now we are able to define the electrostatic field. So the field is something that can be defined anywhere within the space. A field represents some physical quantities. For example, we can define temperature field, wind speed field, force field. We can divide the field into two parts. It can be a scalar field, for example, temperature field, or we can also define pressure field, and it can be a vector field, for example, electric field or a magnetic field. So whenever we have a positive charge, then the line of forces from the positive charge is evolving from positive charge to the outward direction. And so the direction of electric field can be found through um, these line of forces. And if you have one positive and one negative charge, then we already know that the positive charge is considered as a source charge because line of forces is evolving from this charge, and negative charge is considered as a sink charge because all of the line of forces is synced to this negative charge. So when we brought a positive charge and negative charge towards each other, then all line of forces evolving from positive charge sync to the negative charge. Therefore, previously, as we have a line of forces is uniformly distributed around the positive charge, so in this case, the line of forces is modified itself because of this sync charge. And on the other hand, if we have a two positive charge, because the same charges repel to each other, then the line of forces is also repel to each other. As I told you that the direction of the electrostatic field can be found through this electric lines force. So if you look here, that the direction of electrostatic force is changes around this positive charge and also around this positive and negative charge. So electric line of forces is being modified accordingly uh, when we bring some two positive charge or one positive charge and other negative charge. Now let's move on to some properties of the electric field. Field lines never intersect each other. Field line spacing give the strength of the electrostatic field. That means if we see here that at closer to the positive charge, then line of force is closer. Therefore, we call it the electric field intensity is higher at close to the positive charge. However, if we go far from this positive charge, then the spacing between uh, two lines is larger. That means the intensity of the electrostatic field is weaker far from the positive charge. The field lines is directly proportional uh, to the to the magnitude of the charges. So if you have a larger the charges, then we have a large number of electrical line of forces. Field lines always start from a positive charge and always sync to a negative charge. As with the electric force, if there are several charge objects, the net electric field at a given point is given by the vector sum of the individual electric fields. And mathematically, we can write is like this. And this is also called a superposition principle, which we have already studied in the case of electrostatic force. Let's have a look at a very quick problem. Calculate the electric field at the electron's distance away from the proton in a hydrogen atom, and the radius of the hydrogen atom is 5.3 10 raised to the power minus 11 meter. In the previous lecture, I have given an idea about the structure of an atom, that the atom consists of the central core nucleus and the um, electronic cloud around the central core nucleus, which is called electron. So if you look at here, this is the simplest atom and the smallest atom, which have only one proton and only one electron. So in principle, this is the nucleus, and this is electron, which is actually revolving around uh, this positive charge. But keep in mind that the radius of this electron is always constant and given here. So we have two charges. One is positive at the nucleus and other is negative. So the two charges and the distance is also given between these two charges. So in order to find the electric field because of this nucleus on this point can be determined through this equation. Again, this is K is the Coulomb constant, Q, which is the source charge, and R is the distance from source charge to the point where we intend to find electrostatic field. So if we substitute the value, uh, so K has a value of 9 into 10 raised to the power 9. Electronic charge is 1.6 10 raised to the power minus 19 Coulomb, and this is the distance from source charge to the point of interest, which is 5.3 10 raised to the power minus 11 square. So if you solve this number, we will get electrostatic field 5.1 10 raised to the power 11 Newton per Coulomb. If you compare this number with the daily life some experiment, for example, air begins to break down and conduct electricity at about 30 kilovolt per centimeter, or 3 into 10 raised to the power 6 volt per meter. As I mentioned before, that volt per meter is also a unit of electric field, same as the Newton per Coulomb. So if we have this number of electrostatic field, then electron can conduct even in air. Generally, air gives an infinite resistance, but electron conduct within an air if we have this amount of electrostatic field. But if you look at here, this is a very huge number compared to this number. So um, in an atom, we have a very strong electrostatic field so that electron is bound within this nucleus. Another problem, how far apart must 2 point charges of 75 nanocoulomb? Nanocoulomb means 10 raised to the power minus 9 coulomb, typical of static electricity, to be have a force of 1 Newton between them. So this is our equation. This is our Coulomb law, and by just rephrasing this equation, so we can write the distance between the two charges in terms of the square root k, q1 and q2 divided by 4. Substitute numbers given in this problem, and we will get the distance between the two charges would be 7.1 millimeter. Let's have a very short quiz. Two equal but opposite charges are placed on the x-axis. The positive charge is placed at -5. So here is the negative x-axis where we place a positive charge, and a negative charge is placed at x is equals to +5 meter. So this is the point where we place negative charge. So question is, what is the direction of the electric field at point A? So we have in fact 2 points, A and B. So A is on the vertical axis, and B is located at the horizontal axis. So in first questions, um, we need to find the direction of the electric field at point A. So as given here, that this is the position of a positive charge and this is a position of negative charge. I already mentioned in the previous slide that if we have a positive charge, then line of forces is evolving from this positive charge. That means if you find the direction of this positive charge at this point, that must be in this direction. And similarly, if we have a negative charge here, then negative charge is a sink charge, and the line of forces is move into the negative charge in any cases. So if we need to find the direction of electric field, that means the direction of electric field at this point is somewhere from this point to that point. Answer would be right. And second question, what is the direction of the electric field at point B? So again, because this has a magnitude of a positive charge and this has a magnitude of a negative charge. So if we need to find um, direction at this point, we just need to add vectorially the magnitude and the direction from these two charges. So your answer would be left in this case. Now again, in this case we need to find a direction, but keep in mind in this case we have two charges. So in order to find the direction at this point, we first use a superposition principle. Two charges Q1 and Q2 fixed along the x-axis as shown produces an electric field E at point 0D. That means, this is the point of the 0D, which is directed along a negative y-axis. Therefore, um, which of the following is true? Both charges Q1 and Q2 are positive. Both charges Q1 and Q2 are negative. The charges Q1 and Q2 have opposite sign. Let's see one by one. If both charges are positive, then in this case, if Q1 is a positive, and then the direction of, I'll just draw a direction from this. Q is something like this, and the direction of Q2 at this point would be here, for example. So in both cases, the net electrostatic field is somewhere between this point, which is of course not correct. And in the second case, if we have if both has a negative charge, then the line of force is toward. And the net charge of both would be somewhere in this direction. So the correct answer must be B. So this is our correct answer. Another quiz. Three charged particles are placed on a straight line as shown in a figure Q1 and Q2 are fixed, but Q3 can move either left or right. Under the action of the forces from Q1 and Q2, Q3 is in equilibrium. What is the relation between Q1 and Q2? So now let's find the distance from Q1 to Q3, which is x plus x is equals to 2x. And the distance between Q2 and Q3, which is given here, is x. So in order to find a force from Q1 to Q3 and Q2 to Q3, we just use Coulomb's law. But keep in mind, in order to keep this Q3 is in equilibrium, the both forces from Q1 and Q2 must be equal to each other. So let me write a force between Q1 and Q3 is like here, K Q1 Q3 divided by two x square, and that must be equal to the force between Q2 and Q3, which is here K constant, Q2 Q3 divided by x square. But keep in mind, if both charges are positive, then this has to be moved away from this point. So in order to keep this Q3 in equilibrium and fixed at this point, therefore Q1 and Q2 must have an opposite sign. So either if you take this positive, then Q2 must be a negative sign, or other way around. You can also take this is positive, therefore Q1 must be a negative. So any one would be taken as a negative, so that uh, force from one charge would be attractive and other charge must be repulsive. Therefore Q3 would be in equilibrium. So I'll just substitute negative sign in one side. So let me cancel something in these equations. So K would be cancelled and Q3 would be cancelled, X would be cancelled. So finally we can write is Q1 is equals to minus 4 times Q2. So C must be our correct answer in this case. Okay, another quiz. 2 point charges repel each other with a force of 100 Newton. One of the charges is increased by 10% and the other is reduced by 10%. The new force of repulsive at the same distance would be C.